All right, so we're going to first start with we're actually going to go in a little bit of a different order because normally we talk about, normally we talk about collecting data first, then analyzing it, then making conclusions from it. You need that too? But we're actually going to talk about analyzing first. And when I say the word data, I am talking about information. That's what that means. Usually it's in the form of numbers, but it doesn't have to be. And we collect data on individuals. Now, individuals, you would think, are people, but actually they are people, animals, or objects. So like if we're doing a quality control inspection on some type of product, that product, I know it sounds a little weird, would be called an individual because it's an object. And what are we interested in about individuals? Well, we're interested in their characteristics, which we refer to as variables. Squeeze that in there. So, you know, things like heights and weight and sex and ethnicity and things like that for people. And for animals, I mean, it should be height and weight. For objects, usually it's things like height and weight. Now, there's two main types of data. One is called quantitative data. And if you think of the word quantity and the word quantitative, it is data that is numerical. It's numbers. Which means the values have an inherent order. Or another way you could think about it is quantitative data we can average. So for example, or a few examples, height. Because it comes in the form of numbers and we can average height. Weight. Marks. Those are just a couple of examples. Anything that comes numerical. If it's not numerical and we can't average it, it's called categorical data, where the data are categories, okay? And it doesn't have an inherent order. Or we can't average, or it doesn't make sense to average. It's useless information if you try to average it. So categorical data examples would be things like eye color. It's not numbers, it's words. Ethnicity. Sometimes it contains words, or sorry, sometimes it contains letters, but it doesn't make sense to average it. So for example, like postal code. Yes, it contains numbers, but it also contains letters, and you can't average a postal code. It doesn't make any sense. And it doesn't really have any inherent order either. So that's the difference between quantitative and categorical data. So just as an example, here we have some data on 3 students, 3 individuals. And there's 4 variables that are describing them. Okay? And I want to know what type of variable or data is each variable. So height, would it be quantitative or categorical? Quantitative, because it's numbers and you can average them. Dominant hand, categorical. It's not numbers, it's just 2 words, left, right. I suppose it could be a 3rd word if you're ambidextrous. Final exam score, quantitative. And postal code. Well, I sort of gave you these ones as well. So even though it's got numbers, can't average it, it's categorical. We are in this unit going to look at analyzing both types of data because we analyze them in different ways. And by analyzing, I mean finding certain measures about the data, graphing the data. Well, we use certain measures when it comes to quantitative and different measures when it comes to categorical. And we use different graphs as well for each. But we'll talk about that later in this unit. One thing, though, that you should always be careful of is misleading with data, okay? Which is often done. People twist data to fit what they want to say. And they can do it in a variety of ways. So we're going to look at specifically graphs, how you can mislead with graphs. Well, there's different ways you can do it. Graphs have a horizontal axis and a vertical axis. It may not have any axis labels, or it may not have any scale. If it does have a scale, it may cut it off. Like normally, the y-axis, especially the y-axis in stats, should start at 0. But sometimes they may start it at a weird place, like 50 or 70, because it makes the data look different than if it started at 0. And we'll see that in a few examples. Or it may use pictures for bar graphs, which is something called a pictograph. And that can be misleading. So let's look at this first example, which is a pictograph. And this is Kobe Bryant's made shots and assists, his average per game. So his average made shots and his average assists. What were his average made shots? 10, because it goes up to 10. And his average assists? 5. So how much bigger is 10 than 5? How many times bigger? So it's twice as big. Does that large basketball look twice as big as the smaller one? No, it doesn't. It looks like you could fit about 4 of these Looks like you could fit about 4 of these in here. So it's making it look as if he made a lot, his average of made shots was a lot higher than his assists. Makes it look like it was 4 times as many, but you guys all read the vertical axis, which said it was only 2 times as many. So the width of the pictures, or of the basketballs, make it look like he had 4 times, about 4 times, as many made shots as assists. When really it is 2 times. When in reality, it is 2 times. So that's the problem with pictographs, okay? Is that the widths are different. And because the widths are different, it makes it look like the bigger ones are much bigger than the smaller ones than they actually are. How can we correct that? How can we correct a pictograph? Well, we can do a bar graph. So we could have done it like this. And I'll just sketch it. So we got 5, 10, and this is his average. And instead of putting pictures, we would put bars. So for his made shot, we put a bar up to 10. And for his assists, we put a bar with the same width separated from the other bar up to 5. That's how we could correct it. Because the widths of the bars are the same, so it's a much more accurate graph. Okay, this is called the bar graph. We'll get into different types of graphs more in this unit. But you can even mislead with data with bar graphs. So here, the second example, Chevy builds the most dependable trucks. And it says more than 98% of all Chevy trucks sold in the last 10 years are still on the road. Whereas with Ford, it's lower, Toyota even lower, and that's Nissan, is even lower. And it makes it look like Chevy is, well, it certainly makes it look like Chevy's substantially better than Nissan. Well, what's the problem? Yeah, it starts at 95. So it makes, so the scale, or sorry, because they didn't start at 0, it makes it look as Chevy is way more dependable than Nissan. Whereas if we did a bar graph, a proper bar graph, and I'll write in here later. So if we did a proper bar graph that started at 0, so we'd have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%. So I'm not going to label every notch. So 20%, 40%, 60%, 80%, and 100%. Well, we got Chevy, which is close to 100 at 98%. Then we've got Ford. It's actually a little over 98%. We got Ford at 97.5%. So a little bit lower, but not much. And then we've got Toyota at a little over 96%. And then finally, we've got Nissan at a little over 95%. Those bars are probably even closer in height to each other. But you can see, if you actually started at 0, now there's not a big difference. Okay. Yes, Chevy is a little more dependable. But when you look, when they didn't start at 0, it looks a lot more dependable. So the y-axis didn't start at 0. Making it look like Chevy was way more dependable, especially than Nissan. Okay, so that sort of takes, that's really all I wanted to talk about, was just a few terms that you should be familiar with in statistics and how data can be misleading. Most of the lessons come with what's called a discussion. So I'm not going to, I'm not going to write out things on here. We're just going to discuss them. There are written answers in the completed notes on Teams. So, but I think it's worth just talking about them. Here's a couple of graphs. Figure out how it's possibly misleading. So here, graph A was presented by a Republican congressman during a hearing. And this graph represents the cancer screening and prevention services, which has gone in what direction over the years? Down. And yet abortions have gone up. And it looks like the cancer screenings have gone down by the same amount that the abortions have gone up. But is that the reality? Why? Oh, this is the x-axis. Yes, but it does give you some numbers. Yep. Yep. Yeah, like it looks like they're going up and down the same amount, and yet this went down over 1 million, whereas this went up less than 150,000. So yes, cancer screenings have gone down, and it looks like they've gone down substantially, but it also looks like abortions have gone up substantially. When if we put this on a proper scale, we would find that really it doesn't. Okay, so this is misleading. This is suggesting that, oh man, you know, the increase in abortions, it's just as bad as the decrease in cancer screenings, when in reality, it's not. How about the second graph? This was from a Democratic House Political Committee committee saying, thanks, Joe Biden. And it's about gas prices from, oh, looks like over a week. Barely went up. Yeah, it only went down by 2 cents. Like, what's the problem with the y-axis? Where should it start? It should start at 0. And if you started at 0, you could make another line graph, and you would see that it wouldn't be as sharp as a decline. However, because they started at 37? 340? Okay, I'll take your word for it. Yeah, it's a little tough to read. But they didn't start at 0. So it makes the decline look much more significant than really it is. Okay. But these are the kind of things that are often used by people, especially graphs, where there are little tricks you can do to make your point more significant than it actually is. All right, so that's that. Now, because this is an AP course, I really don't have due dates on practice questions I assign. What I generally do is, and especially since we have stats 3 days in a row, so it's kind of, we may want to space it out a little bit. But basically, everything I do this week and every practice I assign this week should be done by next week. So like we'll do 3 lessons this week, and the practice should be completed by next week. And then I would come in on next Tuesday and say, okay, those first 3 lessons, 1.1 to 1.3, are there any specific questions? And just to show you, most of the questions will come from a textbook that I've scanned on Teams, but occasionally I will add some extra questions. So with these practice questions, there are these from the textbook, and then there are a couple that I've put on here that you can answer directly on here. So how do you find these things? Well, Teams. Stats, class notebook. Okay, so here's how you find them. So you go to your course or your content library, and I've split every unit up into Unit 1 notes and Unit 1 exercises. Okay. So for the practice questions, you would go to Unit 1 exercises. And I assign questions from the introduction exercises as well as section 1.1. So let's try this. There we go. So to find the introduction questions, what's going on here? I guess we got to do it this way. You would just go here. The introduction questions were 1379. So you would go here, and then you would see all the questions here. And if there's a question number in bold, that just means it's a multiple choice question. That's all. To find the solutions, go down to the bottom where it says Unit 1 full solutions, and then you would have to scroll down a little bit. So here, well, you don't have to scroll down much in this one, but introduction exercises, here are all the answers. And then if you keep going, section 1.1, well, those are check your understanding questions from the textbook. We don't do those. So you'd have to scroll down till it says section 1.1 exercises, and then you'd find the solutions there. Okay.